Hello. So I'm going to be talking about the demand side, reducing demand, and a wonderful project we've gotten from Pierre to do the following. It's $1.6 million, and so it's very welcome at this time. It's called Changing the Rules, and it's some innovative low-energy occupant-responsive HVAC controls and systems. So the occupant-responsive is the key thing that you're going to see in here. And the changing the rules applies to two types of rules. One is rules of thumb. And rules of thumb are what the building design industry relies on to put buildings together. Many of them have no history, they have no scientific basis, and they just kind of have implanted themselves in the culture, and they are used without much question. So those are things we need to address if they are not beneficial to our purposes. And the other the rules, of course, are the standards that buildings have to comply with, like energy standards and professional standards. And so we're dealing with both of those in this project. The team is our CIEE, who's putting on this conference, our Center for the Built Environment, the EECS program, and Taylor Engineering, who's a small but extremely influential design firm that's very involved in ASHRAE and Title 24. So our project is to come up with three innovation components that I'll talk about. They're to reduce the energy use and to improve occupant comfort at the same time. You can put the priorities either way you like. In combination, they're supposed to, the three components, to address some major control problems that exist in a large majority of existing buildings, including new ones that are being built. And we also want to enlarge the role of occupants and operators in the control of buildings. And so those two desires or intentions kind of apply to energy and comfort as well. These are the innovations. One is low-energy personal comfort systems, which you'll see some examples of. And then in control improvements, especially to your most conventional kind of buildings, which are VAV or reheat buildings, to eliminate widespread dysfunctional behavior, which goes on without people knowing about it. And then finally, there's advanced information technologies that will allow the occupants to involve themselves with the variable air volume systems directly and get some kind of personalized control from it. Now, these may seem like strange bedfellows, but in fact, number two is needed to make any implementation of one or three really save a lot of energy. You can get comfort, you can get pleasure out of the occupants, but to save energy, you've got to have a building that's kind of functioning in some reasonable way. And so we need all three of these, and this is why we put them together in the proposal. So I'll start with the personal comfort systems. And these are things where it's going to either come out of your workstation or out of your chair or out of some place very close to you overhead, which will allow you to tolerate and feel good in higher and lower temperatures. So you'll see that the different systems we've got give us a range that's somewhere on the order here of 64 or even down to 61 degrees, up to 86 degrees in some cases. And they involve this is thermally addressing the human being in the right places in the right way so that they don't feel uncomfortable. Now, CBE, together with SPEED, has implemented several field interventions here on campus in order to prove the benefit of these things. And one of them is going on right behind this screen over here in the Citrus offices. And I went back there just before there and actually grabbed from one of the occupants their chair, which is the chair we've given them. And this is the one that I'll describe next. This chair has heating, which is a red light, and cooling on the blue light, and has an occupancy sensor, so I had to push on the chair to make it go on there. It runs on a battery, and it heats and cools people. It'll run for 3 or 4 days, and then is recharged at night, so you don't have to have a cable. It has user-adjustable heating and cooling. It's a chair. It actually does everything. You can adjust it and do various things with it, but it works very well. And what you see down there in the lower right is that the maximum heating power for this chair, to get you down to 62 degrees, comfortable, is 14 watts, and the cooling power is 3.5 watts. And you can try this out after the meeting. It's a phenomenally effective chair, running at basically no power, and with it, we hope to accomplish energy savings in the building. I'll try to describe a couple of other systems that aren't quite like the chair. They either heat the feet and cool the face by a fan system. This is a combination of things which we've also designed and made and actually built 105 of these units, also being tested on campus. There's a fan unit that comes out of a nozzle. It's supposed to be quiet. You don't feel it except when it comes at you. It has an occupancy sensor down the nozzle, so if you're not in front of it, the fan turns off, and you save yourself about 1.5 watts. Down below, there's a Footwarmer thing with a foot pedal. It heats your feet. You get instant feeling of warmth if your feet are cold in a place. The combination of these two things are controlled by the knob that's on the fan unit. So if this is going to work, yeah. So this is the heater, this is the cooler, and this is the heater here. And the nice thing about this thing is that there's a computer in there, and it can tell the building operator, ideally, what the temperature is in this fan. There's a thermometer in there. And also what the settings are on the two knobs. So if all the people who've got these things throughout the space, you would have like thermostat on every desk, and you'd also know what the people are. If they're all calling for more heat or more cold, you might be able to do something with your main system based on that kind of granular information. Sorry. The thing also tells the occupant various things. This is a thing that will pop up on their computer because that's how we transfer the data in and out, is through their USB port. We have another thing. It's a leg warmer. This works very well for women especially, who tend to have thinner clothing on their lower legs and lighter weight shoes than men. And this tends to run when it's operated. Again, it has an occupancy sensor, but it's about 50 watts. So it'll do the same thing that a 1,500 watt heater will do, but actually more gently and more efficiently. But you do have to have it well designed. It has to have that enclosure. Okay, this is the benefit for this type of thing, and it's remarkably large. If you can widen the temperature set point from the conventional 72 to 75 that you find in U.S. Buildings, though I must say now they're actually often just a single unitary point, you tend to save somewhere on the order of 5 to 8% of your total HVAC energy for each degree that you can either increase or decrease the set point. That's a huge amount. So you can see totals here that are running up to 40%, especially in this area. And then the comfort is good, and it because it expands the set point, you can then enable more efficient types of HVAC systems on new buildings. At least you could allow naturally ventilated buildings, or buildings that had cooling towers instead of chillers, or buildings that had evaporative cooling systems or radiant cooling, which might be very slow acting. It might be cold in the morning. Well, if you've got the Footwarmer to take care of that problem for an hour or two, then that type of building will work, and then you can save energy by designing those kinds of buildings instead of VAV buildings. At any rate. So then the other thing that we've talked about is that these sensors in these widely distributed devices can add more granular information to buildings. So here's one building. This is the Doe Library Annex that we've been studying with these units, the Footwarmer fan units. We've been metering the building in great detail. Surveyed the occupants before and after. I've got in there on the slide that we've also done the Brower Center down on Oxford Street, which is a highly efficient, radiantly heated and cooled building. And in this case, this was a winter test. We set the temperature down to 66 degrees and then back up to 70 where it had been for the previous 5 or 10 years fixed. And we get these big savings out of the test and the various changes made in the tests. It's 20 or 30% savings. So that's the potential, and I think we'll see this on the cooling side too. The hot weather is coming and the tests are about to be made for the cooling part of the system. So now we're going to just describe briefly this thing about the control improvements. So we've talked about the narrow temperature deadbands, which you can maybe offset with the personal comfort systems or even other things. Minimum ventilation airflow set points. These are also, by rule of thumb, have been set up so that the minimum airflows allowed out of VAV diffusers are often at the range of 50% of their maximum. They just throw away half of their throttling range because they feel that there may be poor air distribution coming out of the diffusers. Now, when you have these high flows and there might be low loads in the space, you end up with an excessive amount of airflow because your minimum has been artificially maintained very high. There's also a lot of fan energy involved and heating energy. So we've recently completed studies that have shown that you can reduce the levels down below 50 and 30%, down to 20%. In fact, this is now in Title 24 as a result of this work. But you can actually go below 20%. You go to 10%. You're still way above the ventilation limits in most cases. So there are other things that we would want to change. So I'll talk about this a little bit in the next few slides. But the other things we are interested in are various ways of more intelligently resetting the supply air temperature so your chiller doesn't have to run as much, finding rogue zones that may take command of the whole building and force the supply air temperature or the supply volume to be too high as a result of a bad reading or something wrong, and fighting zones where you're heating and cooling at the same time, and this goes on all the time. So I'll talk a little bit about just the low minimum. The low minimum reduction is really important. So here we've got 10, 20, and 30%. This is the minimum flow that's capped. You can't go below that. If there's no load in the space, you don't need a flow. But if you're capped at 30%, you're going to be pumping air in at whatever the supply air temperature is. You may have to reheat it. And odds are you'll certainly use energy. You can see your savings in this case are, again, in the 30 to 40% range. But you'll also very likely overcool people. And this is something you can see here. This is one of our new buildings. This is our champion for energy consumption on campus, Stanley Hall. It uses somewhere, I understand, close to 20% of campus energy. Here's a couple building or rooms in this building. Over here is a room with one occupant. There's 106, and then there's 106E with two people. Over here you can see diffusers in the ceiling, and they have plastic taped over this one and some fake cardboard on that one. That's to keep the cold air off the people because looking at the terrible control system in the building, but you can see here that in these zones, which got 2 people and 1 people in it, you've got on the order of 900 and 300 CFM going to the building. Now, for one person, you need 15 CFM. So we're running 20 times the air that we need. And it's cold air because the building is essentially a kind of an internal-dominated building. So this building has got its dampers closed. It's straining to provide this huge amount of air, pre-cooled air, to just few poor people who are sitting there being frozen. And there's a lot of complaints about it. So this type of problem happens here, but it happens everywhere. We did a big study in the Yahoo campus, the whole 7 building campus, a big building called the Ferry Building in Martinez. And in this case, by reducing the minima from 30 down to 10%, we not only saved a lot of energy, which you'll see next, but we reduced the complaints in half. So this is the dissatisfaction with the thermal environment. So, wow, this is great. You know, you have a win-win situation possible. Here are the savings that we saw. These are all the Yahoo buildings. The only one that didn't come up with a big saving was had a data center in it. But the others are all finding large savings. Yeah, there they are. So implementing that type of stuff is going to be part of this project. We want to make sure that in the end, the rules of thumb that are in the way, that are standing in the way of progress, or the way of intelligent operation, will be kind of erased in standards and codes, and there'll be requirements that building controls operate with better control sequences. So finally, EECS has developed this wonderful platform that we intend to implement all this on. It's called SMAP, and it's been mentioned. The demand response people are using it. The grid synchronization program are using it. It's a big database program that allows very quick data access and visualization, among other things. So you can see here that it can also be used on top of building control systems to actuate the actual components of buildings remotely. So we are able to get into certain buildings and change things ourselves from our office that would normally have to be done by somebody in the basement or in the campus control part of the building. And so we've arranged to have this right to do this, and we're able to actuate. But in the end, we will want to build the logic of better building control into SMAP and make this available to the public. One thing we've got already is this fabulous data analysis and sensing and reporting capability where you can look at what's happened the day before in seconds. And this is extremely valuable. The other thing you can do with SMAP, and the EECS people have already done this, there's a startup been launched about this, is to use things like smartphone apps to allow individuals in the building to kind of talk to the diffuser that's nearest to them and make it do what they want. In some cases, to come on with a burst, and it would go on for a short period of time and go away. It has all sorts of smart behavior. Very exciting stuff, allowing dynamic interaction between a person and their central system without requiring a vast amount of energy from the central system to accommodate that interaction. Out of that, it's pretty much the same thing as I claim for these things. If you have these smartphone apps going and you're talking to the central system, you can also find out situation. You can poll the occupants, find out who's there, what they're calling for very quickly, and you can provide more feedback to the central system. This is just a couple of, this is something you pull up a couple of plots from the Doe library, just showing that the system's running the same on the weekends as on the weekdays, and in this case there's no reason for that, but it's traditional. Here's the SMAP as a development platform for running the apps and things like this. In this case, there are some fighting zones that were causing improbable operation in the building, which the SMAP thing can identify and pull out for you. So we're coming up. This project's just beginning. We're coming up with a number of demonstrations, and some of them are done by this project, and some are done by parallel projects. And one of them I want to call out is the SPEED program that Carl Brown operates here on this campus, where we're demonstrating these things. We also involved in CIE is involved with implementing the UC Berkeley operational excellence management program, where we're hoping maybe we can start incorporating some of these ideas right from the beginning, and then we can use them for our field studies and demonstrations. I think that those would be the main points on that. And so finally, the important thing is that we get this stuff published, of course, but implemented in the codes as appropriate. As I mentioned, the Title 24 Energy Code has now VAV requirements for new buildings that the minima are not set 30 to 50%, but have to be at 20. We hope to go further. We know that already. Title 20 is appliance code. I don't know if they will apply to chairs. We'll see. ASHRAE Standard 55 is the indoor environmental standards, and we've got a lot that we can do there to improve that. It's just become a mandatory. It's been written in mandatory language. It's just become something that can be referenced by codes for the first time. Standard 90, Energy Standard, and 189 for air distribution are already in our vehicles for this. And I'm not sure. We didn't promise anything for LEED or the ASHRAE performance measurement protocols, but we may work on those too. So that's where we are right now. We're bright-eyed and bushy-tailed. The project is just launched.